it's okay. It does the trick. But it's actually not a bad idea. It really, the thing is though, I walk around so much that it's really more useful to have a human being. I haven't yet had anybody fail to volunteer. I have had people fail to actually record it by not pressing the button correctly. That has happened, yeah, but yeah. I mean, I'm okay with a little crowdsourcing. Is the crowd like the source? Hello, good morning, everybody. How are we doing today?
Good. How are you?
Good? Okay. So, course-wise, I don't think we have any announcements as of yet. We're currently in the process of getting the Jupyter server set up. We should have that up and operational for you guys early next week at the latest. Possibly by the end of the day. We'll see how things go. And yeah, that's about as far as that goes. Any question, comments, or concerns about anything in particular or in general? Yes, sir.
Where can we find the slides?
The slides are on Avenue under Content.
I've been looking at them,
Well, I mean, I'm pretty sure they're there.
Yeah, they're there.
And,
Yeah, they are.
oh, that's my, there we go. Shoot, all right. Let's take a look at Avenue just to make sure. Oh, no. Now it's being slow on me. All right, we'll just, they're there, I'm sure. And if not, send me an email. We'll get it all fixed up. So, with the assent of the audience, I'm sure all or most of you have heard at this point of the passing of Queen Elizabeth II. And I thought it would be nice if we just had a moment of silence in class right now to commemorate the life of a woman who served her people for a very, very long time and, you know, is the head of state of the country that we're currently in. So the respectful thing to do would be to stand for the moment of silence. Okay, and we'll start it now. God save the king. So, might as well keep going then. Oh, I was on the previous slide actually. Yeah. So, just to recap briefly, last time in class we did a somewhat complicated example pertaining to a bisection method for finding the x-intersect of a monotonically increasing function on some interval. This program was reasonably complicated. it is unlikely, like you will not receive through in-class instruction all of the pieces that were used to produce that example until we have covered, I think, topic 4 or 5, the one on functions, abstraction, and recursion. As in the course of that example, we were passing a function as an argument to a function, which is something we'll be talking about when we talk about functions. So it was not my expectation through that example that you would understand all of it. My purpose there was to give you an example of living code, right? So that you can kind of get the flavor of what programming looks like, you know? If you're one of those people who has come to programming later on in your existence and are still somewhat unfamiliar with the ins and outs. So, we were talking more generally about algorithms, properties of algorithms, things that are important, what an algorithm is, all kinds of interesting things like that. It turns out that algorithm is actually a person's name that's been bastardized and Latinized. The medieval Islamic scholars were really knocking it out of the park on like the development of mathematics, and there is a reason that we all use Arabic numerals. So it's interesting. The word algebra has a similar origin, but yes. So algorithms, very good. So algorithm is a very general term. In its most general sense, it is any process which permits calculation. So all of the processes that you've learned through your grade school and high school careers for, you know, for example, calculating a division by long division, something like that. These are all algorithms. However, in order to produce an algorithm which is useful for a computer, it must have certain properties, right? You must be able to execute it mechanically. So, in theory, algorithms can exist which require, shall we say, the creative input of the human mind. The whole purpose, or the, shall we say, computers being completely incapable of any degree of creativity whatsoever, aside from the illusion of creativity produced through statistics. When you write an algorithm, it must be executable mechanically from start to finish. There must be no step that requires human intervention or human creativity or any kind of human intervention, shall we say. Now, that's not to say that computer programs do not require human input, right? Most useful computer programs will require human input at some point, but not to perform the calculation, normally to provide the inputs to the algorithm, right? So, in order for an algorithm to be executable by a machine, and computers, while they are, you know, many people sort of think of them as this mysterious and magical entity, they are in fact only machines. Very complicated machines, but machines nonetheless. Each step must be both precise and effective. So precision in this case means that the instructions must be completely unambiguous. There must be no leeway for interpretation with respect to a particular step. If we go back to our, you know, baking a cake recipe example, anything that's been encoded in natural language will be subject to a certain amount of interpretation by the reader. This is just, you know, due to the inherent degree of subjectivity built in through the imprecise application of, you know, these pretentious apes who started building buildings and such, meaning human beings. The computer, fundamentally, all programs will break down to machine code instructions, right? That means that number one, your program must be expressible in terms of those machine code instructions, and you must unambiguously be able to follow a sequence of those same instructions. So, that's what is meant by precise. These instructions must follow unambiguously one from the other. This is often set this is a precondition of most computer architectures. The way that the CPU is set up itself determines, you start at one line, then you go to the next, then you go to the next, then you jump to here, then you jump to there. All of these are instructions in the CPU. Also, the algorithm must be effective. Each instruction must be executable by the underlying machine. So, what this means, and I unfortunately see quite a lot of this in beginning programming students. I sometimes see someone taking programming constructs and putting them in the middle of what appear to be English sentences with intended English semantic content. This is absolutely not how programming works. You should think of every symbol that you enter into a program as being, code for some series of machine instructions, not the other way around. The machine instructions do not resemble human speech. Human speech is, brought down out of the great levels of poetry and literature down into the base and earthy realm of pure mathematical reasoning, right? So when we say for, that means something very specific in a programming code, or in a program. When we say if, that means something very specific in a program. Many novels have been written on the basis of the two-letter word if, but in programming code, that is specifically an optionally branching instruction. It is always, always, always instructions. The thing about Python as a language is it somewhat attempts to obfuscate that fact. It's trying to hide things behind words as if they weren't just instructions in a misguided attempt to try to be gentler on people who can't program. I personally think that this is a misguided, design feature of Python. I think it would be much more simple to understand the program if they sort of tried not to cloud it with the, eccentricities of natural language, but, it is what it is, and Python is the language we are to learn. You will, by varying steps, come to learn in this class that I do truly loathe Python as a language. This will become revealed in various ways. Actually, I'm also teaching a C class today, too, the second-year mechatronics class. This semester, anyway. C, and they've only done Python in first year, and I said to them, it's time to put the children's toys away and learn a real language, and I meant it. So, regardless as to what everybody who's not a computer scientist thinks, everybody seems to be in love with Python for some gosh darn reason. I can't understand why. So, as an application of precision and effectiveness, I'll just give you off the top of this that everything in here can be executed by a computer, as we demonstrated previously. However, there is an ambiguity embedded in this description of the algorithm. Can anybody find it? Yes, sir?
The input?
The which?
The input.
The input? Not what I'm looking for. Yes, sir?
The intervals on 3 and 4. One says less than equal, and the other says equal.
Correct. So if we take a look at these conditional statements, 3 is to activate if f at m is less than or equal to 0. Otherwise, f at m is greater than or equal to 0. Both include the case where f at m is equal to 0. So the question would be, which one of those do we execute in the case where f at m is equal to 0, right? Now, you kind of avoid this problem, fortunately, with the if and the otherwise, right? So, similarly to real programming code, when you have a conditional, the conditions of that conditional statement are executed or tested in the order in which they occur. So, if this were an if statement inside of programming code, this condition would be tested first. If it came true, this statement would be executed, and then this one would not be executed. It would not even be tested, right? Because they're called if-else blocks, and only one of them will be executed as control passes through that block. Does that make sense? We'll get to how if statements work in sufficient detail. Question?
Then what, like, if it works like the same, like don't we do the like otherwise if like f at m is like just like greater than 0, like not greater or equal to 0?
That would be a better way to program, in my opinion. That would lead, yes. So the question is, why would we not just change this operator to greater than, rather than have it as greater than or equal to, right? And the answer is yes, that is a good thing to do. You should do that. Despite the fact that this series of instructions has been disambiguated by the fact that it is a series of instructions, it is, in engineering we have this idea of multiple redundancy, You want there to be more than one thing contributing to the correctness of your program. Question, sir?
I mean, normally, wouldn't you just not write the second if f of m is greater than or equal to 0? Shouldn't you just put like an else? Just if it doesn't return true for the first one, then it should just execute the other branch anyways?
This is also the case, yes. Another way of approaching this is to simply provide an else case here. That is to say, leave off this if entirely, and just say if f at m is less than or equal to 0, set a to m, otherwise set b to m.
Yeah.
And that avoids the entire problem completely, yes. That would be the most efficient way of dealing with that. Any other questions? Okay. If you have your hand up and I don't see you, just throw something at me or something. I'll just skip those. So, fundamental questions about algorithms. So we know now, we have some vague idea of what an algorithm is. The entire discipline of computer science revolves around the selection or generation of an algorithm appropriate to the situation you find yourself in. Not all algorithms are created equal. Some algorithms are far, far better than others. Algorithms are a constant area of study and research, not only in the design of new algorithms, but in the evaluation of existing algorithms for their, what we call, runtime characteristics. So, when we are examining an algorithm, fundamentally, we are asking two questions, both of which pertain to efficiency. Well, and then we're also asking about correctness, right? So, if it doesn't do what you want it to do, it's not correct, and that's bad. Moving on. Incidentally, correctness is primarily what you're being graded for. Incidentally, correctness is almost exclusively. Incidentally, correctness is exclusively what you're being graded for. Anyway, so efficiency. When we examine the efficiency of a computer algorithm, we are interested in two things primarily. How much time does it take, and how much memory does it take, right? This is often called time and space, memory being space, roughly speaking. Yes?
Do we get extra points if we configure it for efficiency?
Occasionally, I think there are some bonus marks available on a couple of questions, but primarily, getting an algorithm correct is usually enough for anybody to have to worry about in this class. Although I glossed over it, getting the algorithm correct is like most of the problem most of the time. But anyway, so in general, algorithmic efficiency is a very, very, very large concern. Consider the size of the amount of, like just the sheer magnitude of the amount of data that's flowing in the modern era, right? This would, like dealing with the sort of objective size of the data sphere at this point in human history would be completely impossible were it not for efficient algorithms. Later on in the course, we're going to have an example where we compare the difference between linear search and binary search. Linear search is a searching algorithm where you have a whole bunch of data, and in order to find whether or not something is in that, some individual element is in that data, you in turn examine each element of the data set in order to compare it to the thing you're looking for. If you find it, then you found it. And if you didn't, then you have to go through the whole thing to determine if you didn't, right? That means that in that case, the amount of time it takes to search the data structure is directly proportional to the size of the data structure. Like it's a linear relationship. That's why it's called linear search. The binary search, on the other hand, has certain preconditions attached to it. The data set itself must be in order, but it allows you to perform a bisection analysis on the data in a very similar manner to the first example that we looked at, right? So, rather than having to examine every single individual element in the data structure, you half the portion of that data structure in which the answer will exist if it exists. You divide it by half on each step, which means that if you had something like 10 million things that you had to search, through linear search you would have to examine 10 million individual data points. Through binary search you have to examine like 22 or 23, right? Now that's a very significant increase in speed. So algorithmic efficiency matters. You don't have to like know it now. You'll have whole classes on it. But I just wanted to give you a flavor for that so that you have some appreciation that, like, you know, this is very important. Another thing that's sort of important to mention, just give me one moment, please. Another thing that's sort of important to mention here is that often there's a trade-off between time and memory. It's very often the case with algorithms that you can spend a little bit of memory to do some additional bookkeeping and then gain a whole lot of runtime. And we're going to see some examples of that later on in the course. But where was that question? There you go, sir.
Yeah, I'll just clarify. So we're not going to do like time complexity as part of algorithms.
We will touch on it. We will introduce some definitions, but you're not going to be like. There's no like multiple choice in this class, you know. So no, we're not going to be. I'm not going to require you to perform complexity analyses over data, but we will talk about it. And it will be something that is expected of you in later courses. Does that make sense? Yeah. We're just introducing the topics right now. Yes?
I just had a question about binary searching. For binary searching, don't we have to sort the array first before we perform a binary search, or wouldn't that take like a bit of time?
That's an excellent question, although perhaps better suited a little later in the course, but I will answer it anyway. So the question, sorting an array. So in order for binary search to work, you have to have sorted data. Does it not take time to sort the data? And how much time does it take? Some of the most efficient sorting algorithms that we have currently are proportional to n to the power of 4 over 3, I think, where n is the size of the thing that you're sorting. So that is quite a lot more than log base n, or log base 2 of n, which is what I was describing with the binary search. However, if you have a data structure which maintains a property of sortedness, rather than having to sort it before you use the binary search each time, then you absolutely get your logarithmic complexity out of the binary search with, like, basically what you do is you change the insertion operation from a constant time algorithm where you just slap the new element on the end of the data structure and call it a day. You have to actually pick the point in the data where it's supposed to go and insert it at that point, right? And of course, you know, how long does it take to find the correct place? Well, you have to do a binary search. So it's a logarithmic time operation to insert, but through that, you maintain a sortedness property in the data structure over time, which means that you can use the binary search on it anytime you like for that very, very nice logarithmic complexity. Does that make sense?
Yeah, thank you.
Question?
If you have a very big program with many different efficiencies or different aspects of the program which have different efficiencies, like you're saying, is it always best to have the most efficient at each point in the program, or are there times when, say, a particular data structure works best with a different thing despite them not having the best efficiencies, they kind of work together? I don't really know.
There are many, many factors that go into it. Sometimes you're not even concerned about time efficiency. Some computational applications are for very small devices, right? This is generally a domain that we call embedded systems, right? But you know, embedded systems are anything with a processor in it, all the way from kitchen timers to your smartphone. But like, if you take the standard automobile these days, they have like 100 odd processing cores in them now, all of which is an embedded system, right? On those, you're not necessarily optimizing for time. The things that you're performing are simple. What you're optimizing for is memory, right? Because if it's a product, each piece of memory that you stuff into an embedded system is contributing to the cost of manufacture. And you might be manufacturing large product lines, as opposed to pure software, which essentially can be copied for free over the internet, right? So sometimes what you want to go for is the smallest program size that uses the smallest amount of memory, which increases the runtime, right? But that might be the pertinent metric for the system that you're working on, right? But to your question about, you know, if I have a program with multiple algorithms going on with multiple efficiencies, generally speaking, the design principle at play is that the weakest link breaks the chain, or the chain breaks at its weakest link. So, you know, if I have an algorithm, let's say we took the binary search that can process 1 million elements in 23 steps, and we add to that another process which has to process something for every single one, right? Like 10 million plus 23, 10 million and 23. The 23 is a very, very small fraction of the 10 million, right? So essentially the principle is that whatever the largest, you know, factor is will dominate the runtime over time as the input increases. So you really want to address those points in the algorithm that have the longest runtime, because they will absolutely dominate over time. Does that make sense? Cool. All right. So, I apologize for skipping all of the question answer sessions, but we're already behind, so. So, hopefully the class has been interesting, though. So, anyway, so let's talk about flowcharts for a moment. So, the question that we now have to tackle, given that you are absolutely fresh, green young programmers who have absolutely no idea what an if statement or a while loop even is, how do we instill in you the correct way of thinking to be able to program? The first thing that we do is we give you a good visual model of computation which you can resort to in times of crisis, need, or very early learning, which might be the same thing, actually. So, flowcharts, right? The flow of execution through a program may be modeled as the flow through a flowchart, right? So, just a word of warning. This is an island upon which you may find some brief spell of refuge in the storms of your first year program. However, it is a very shallow harbor, and as your ship takes on more cargo, this harbor will no longer serve your purposes. Basically, in order to do well in this course, you need to quickly evolve beyond the need to put everything into a flowchart. The algorithms which you're going to use, even in the middle of this course, will swiftly become too big and cumbersome to be put into visual or graphical form. You're going to have to learn to program in programming code. However, to get used to the idea of programming, this is an excellent tool. So, how will this work? When you see a box, this will indicate a statement. Statements normally are assignments to variables. They are the setting of values in memory. We are going to see how that works in not too long. Subtract v from u is what we're going to be. This is the best of these bullets to describe what that thing will be. Conditionals are also very important. Conditionals are points upon which the execution of a program will follow one of two directions, depending on the outcome of the condition itself, right? So this b here, the reason that it's b is that we put there what's called a Boolean expression or a Boolean condition. Boolean just means resulting in either a true or a false value. You will come to know and love Booleans, perhaps with something not even approximating Stockholm Syndrome. They're actually quite easy and the delight of all programmers. So, this is a condition which will result in a true or a false result, right? This is very similar to the conditions that we described previously. This is a condition which results in a true or a false result, right? F at m is either greater than or equal to 0 or it's not, given that we must have concrete values for m and some, effective algorithm for f which unambiguously calculates a result. Right? So this is a Boolean expression. These Boolean expressions control the flow of the program. Does that make sense? Any questions about that? This shouldn't be too bad so far. So, this should come as no surprise, but since it's a flowchart, you have boxes that follow other boxes. I'm not sure why this needs a slide, except to say perhaps sometimes in the flowcharts we're about to see, these dots indicate the beginning and termination of an algorithm. So, this is definitely the most important slide that we've seen so far. You will need to know and love these constructs because you need to be able to think in these constructs. These are flowcharts which give you the structures of two varieties of if statement and your basic while loop. When it comes to programs, so long as a programming language has conditionals and loops which may or may not terminate, then you can write any program in that language that can be written in any language. That's kind of a weird phrase. So let's say you had a program written in C++, right? So long as your language meets certain conditions, i.e. the presence of the ability to do these operations, that C++ program can be written in your language. It may not be, you may not be able to write it efficiently in your language. Different languages are good for different things, right? But this is a concept that we have known as Turing Equivalents, right? Or Turing completeness. Have you guys heard of Alan Turing?
Yeah.
I should certainly hope so. If not, if you have not heard of Alan Turing is a early to mid 20th century British mathematician who laid the foundational framework for computation as a science and a discipline, and was instrumental in some of the earliest attempts at building electric computers. So, let's dissect these. If B, then S, right? We have a conditional statement. If that condition comes out true, you execute some statement S. Otherwise, execution jumps to after that statement has been executed, thus skipping the statement. So this if B then S allows you to conditionally skip S being executed on the condition coming out false. Make sense? Good. If B then S else T, if you take this one and you put another statement on the negative branch, then you have what's called the if then else statement. Right? Does that make sense? Repetition. While B, do S. Execution comes into the conditional. If this condition evaluates true, we execute the statement S. Rather than flow, then continuing on from that point, we send it back up to before the condition was evaluated. We then re-evaluate the condition and proceed on the basis of that evaluation. So, if this condition never becomes false, you never break this loop. That's the infinite loop that I showed you guys last time in class. While true, true can never be false. So that loop can never be broken, hence you have an infinite program. I had a couple of questions, but I'll start with you because you got me up.
I'm just curious about what if there's like if and else if and else, then how will the structure will be gone?
You take this structure and you create a new instance of it right here. So rather than have T here, you have like B2 and then T and then U coming off of it. That's if, else. That's a 3-branch conditional instruction. Does that make sense? We're actually going to see an example of that in the next week or two. Probably next week. I thought there was another question. Yes?
So each LF statement you make, it's kind of like a staircase, right? It just goes down.
It's absolutely a staircase. And that's the correct way to think about it too. Because if you create a long series of else ifs, right? Then you have condition, 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 condition. The first one gets executed first, and if it comes true, the entire rest of the staircase is not even tested, right? And that is true to how else if statements work. Does that make sense? Good. Now, you can always design the conditions on them such that, so if you want multiple of the branches, for it to be possible to execute multiple branches, it's very simple. Remove the else and just have a series of if statements, right? That removes the exclusivity, and then it'll execute as many of those as are true. Does that make sense?
Yeah, thank you.
Cool. Any other questions? Way at the back, sir, you're going to have to shout. I can hear you okay.
I was gonna ask, initially you said that we're gonna go beyond to a point where flowcharts we can't even design them. Are we gonna initially start by using them, drawing diagrams and
If you need to, then you're welcome to, but if you don't need to, then you can skip that step. It's not going to be required of you that you draw the flowcharts. But if you need to do it, then you should do it. All right? Yes?
For the first selection of the function, you said that it's not such like just give the instruction.
Yes.
In the case of rewriting the code, let's say the statement is false, it's completely disregarding the existence of the statement or is it skipping?
Skipping it is disregarding the existence of it, to an extent. Well, I guess what do you mean by disregarding the existence of?
Because initially the instruction is there, for the sake of the true, they will use the same instruction. But if it's not skipping, it means that because it gives the state. The instruction is still there, but it's just...
Right. It still exists in the program, right? Now, the thing to remember about these constructs is that they might exist inside of other constructs, right? So our if then else, if B then S, that first one, right? That might be inside of our loop. So it might be that we come back to it several times. And the several times that we come back to it, that condition, the outcome of that condition may have changed, right? So we don't forget the instruction itself because it may yet be useful, right? In fact, you wouldn't make a branch unless both branches had some purpose, right? So yeah, we don't forget the instruction itself. The instruction itself will always remain in the program memory. From an effective standpoint, if you always skip the instruction, then it's like it doesn't exist, right? But if you write an if statement with a case that's always skipped, then you're a bad programmer, basically, right? Does that make sense? Have I answered your question? Question? Not in this class, no. You're expected to write Python. Detestable though it may be, you're expected to write Python. And Python is practically pseudocode anyway.
For flowchart wise, is for loop similar to the while loop?
Not in Python. You're probably used to Java. Yeah. Okay, quick tip for all of you like programmers in sane languages. For loops in Python are much closer to a for each loop in something like C# or C++. I don't know if Java has a for each loop, but for loops in Python they're not just syntactic sugar for a while loop with a couple of things thrown in. A for loop iterates over the elements of a data structure in sequence. Does that make sense? Sort of?
Yes.
We'll see a lot of examples.
Okay.
Any other questions? I love all these questions. Yes?
Just to reiterate what you said, you mentioned that if it's else if, you're skipping over the statements, but if it's if, you can go through all of them.
So, yes. In essence, yes. So, got a hair in my mouth or something. Anyway, so for if B then S, right? There it is. Sorry. Yeah, so we skip the statement on false. We execute the statement on true. If we have a whole bunch of these in sequence, you can imagine like this construct being followed by like 5 more. It is possible, if all of the conditions come out, that each one of those statements can be executed, right? By contrast. With an if then else, these two branches are always exclusive. It's always either one or the other which is executed, right? So, if you've got the, if then else, if then else, if then else, if then else structure that I was talking about previously, always only one of those branches will actually execute. Does that make sense? Good. Any other questions? Yes, sir.
How do you display a switch statement?
Switch statements don't exist in Python.
No, I mean,
They kind of do now.
They do
Kind
now?
of. They're structural pattern matching, which is fancy word for switch statements with more stuff. And if elif is basically a switch statement.
No, it's not a switch statement. It's not a switch statement. Switch
It's the
statements
same
are
thing
much
then.
closer to go-tos than anything else. But
Almost get the same thing.
and go-tos are forbidden magic. Just so you know, that is the dark arts. And if anybody uses a go-to in this class, I will fine you. There's a very good reason that we don't use go-tos. So switch statements aren't really, we're certainly not going to be covering them in this class. They did a recent addition to kind of bring them in, but it's not going to be the switch statement that you know and love from C or Java or any of those languages. I think you had your hand up first.
Do while loop exist in Python?
While loop?
Do while.
Oh, do while? No. Yeah. Python has this interesting design decision that there should only be one way to do something, which is right?
Some of them, there's 6 ways to do some things. Which
Well,
is really simple.
it's absolute madness because there is for any reasonably complicated algorithm, there's literally combinatorially millions to hundreds to thousands of millions of ways of producing any particular algorithm. To have the conceit to say that there's only one way to program in Python is ludicrous. But yeah, there's no do while because they were like, a while loop does that, so they did that. The same reason they don't have switch statements. Effectively. Question?
Are we going to learn other packages in Python,
Other packages in Python?
like hiding or mask?
We're going to talk a little bit towards the end of the course about those other packages, but we need to do object-oriented to be able to get there first. So you're talking very late in the course. Okay? Everybody's packing up. I think I still have some time. Let's see. Oh, get your bags back on the ground. We still got 2 minutes. What do you think this is? So, assignment statements. It's very, very important to understand the assignment statement. The assignment statement is like, if statements are one leg of the stool, loops are another leg of the stool, then the third leg of the stool is knowing how to manipulate memory. So, I've mentioned this before, but variables in programming are very, very different from variables in algebra. In algebra, when you have a variable, the object normally is to compute an exact value for that variable, given the conditions on that variable in the form of equations. In programming code, a variable is always a name for a memory cell. A memory cell of varying size, perhaps, but a memory cell nonetheless. The memory represented by the variable is expressed in ones and zeros inside of the hardware electronics of the computer itself. It is not physically possible for a variable to not have a value. It must be ones and zeros, right? Now, that value may not be valuable. It might be garbage data, but garbage data is still one precise and exact value, right? So, you can set the value using an assignment statement. E is an expression, some kind of mathematical expression. X is the memory cell that you are writing the evaluated result of that expression to. Any questions? Yes, sir? Is Python what?
Does Python have addresses?
Python, to an extent, yeah, but not like you can reveal it with the ID function, but it tries to keep all of that stuff under the hood for you. But even if you don't have direct access to pointers or memory addresses in Python most of the time, it's still extremely valuable to understand them. Yes.
So is that like similar to like x equals
No. This is just right. This is one equal sign, not two equal signs. Two equal signs is always equality evaluation. All right. Any questions? All right. Thank you very much. I'll see you next time.